Oh, here we go. So here we are, day 17, and the recording for both classes this morning was unsuccessful, and we ran into problems with PowerPoint. So we're making a brand new recording. And you even get my pictures. So this is last week. This is Kingsburg as you drive down into the village. It really calms you down. And with the stress of this recording, I wish I was there to enjoy it. Unfortunately, I'm in Halifax. Um, and last week, Dora and I took a walk to Felton South, which is a place lots of people have never heard of or seen before. It's across from Lunenburg. Here's Lunenburg. Lunenburg is over here in the picture, if you can see it in the top left corner. And if you look across the water and out towards the sea, one of the last pieces of land you see is Felton South. And the day we were there, the sun on the moss that grows on the rocks here at low tide, bright, bright orange. It was a really colorful day. Anyway, but it's a beautiful day outdoors today too. And let's get on with the show. Look, here we go. So last class, we zipped through quite quickly, but I think we covered the basic stuff of introducing classification problems. It's definitely one of the most common data mining applications when the objective is to try to predict whether or not a transaction, a customer, an activity fits into one of two or more different categories. I say nominal, it could be ordinal categories as well. But most of the time, it's cases where we're looking at just two categories, binary classification, that yes or no. That the others are much more complicated to handle. And one of the reasons why I like it, covering it, even though we don't get into the nitty gritty of the technique and actually applying it, is just giving an overview of the variety of ways you can solve problems. That in so many courses, you're taught how to solve, they say, how to do the calculations for a specific thing, how to find something. But that's the problem has already been defined for you. You have a specific method, and they just show you the mechanical activities that are involved. A computer can do that. It doesn't require any thinking, really. What's important is solving less structured problems. That's in part why I introduced you to the framework of CRISP, of taking from what's the business situation, who's involved, what are their objectives, what are they trying to achieve, what do they think the issue is at the moment. Then we look at what data can be used, because this is a database course, data-related problems. How can data help them achieve their objectives? And we, where can we get the data? What do we need to do to it? Can we trust it? What's the quality of it? And we moved through and we got into modeling. We got into value estimation, where we looked at one particular technique, linear regression, that is by far the most common technique used to address value estimation problems. That classification is interesting because in terms of models, there are many different types of models you can use, different ways you can approach it. And that's the big takeaway here, is that there isn't one way, one best way to do classification. You can approach it different ways, and people use different types of ideas. One of them is to, if you're trying to see, are you in a group or not in a group, to try to estimate what's the chance you belong to that group. What's the probability you're going to renew your cell phone plan? And then make a decision from that. And one technique for doing that, and there's several to do that, is logistic regression. So a formula-based one that's similar to what we use for value estimation. Another approach is to not estimate the probability, but just try to separate the two groups by putting a fence between them. And on one side of the fence are the good guys, other side are the bad guys, but you probably can't build a perfect fence. You're going to get some good guys in with the bad ones and some bad ones in with the good ones, but hopefully not too many are misclassified. Again, though, it's building the fence is like finding a formula. Another approach is one that we use in making a lot of decisions. We think about similar situations we've seen before. How did we handle them? So let's find similar cases from the past and see how they were classified. Were they good or were they bad? That so it at first blush doesn't sound like it's a formula driven one, but we end up needing formulas or some tool for measuring who's similar and who's not similar and who's very similar. Who's the nearest neighbor. So you need to measure nearness, closeness. And so we still will need formulas. But the underlying idea is a very different one from the other two. All three of them are very different. That and in practice, all three have been used a lot and very successfully. And there isn't a best way of doing this. In practice, we normally train uh, each of our models on a data set, and then we keep a separate data set that we're going to evaluate the models with. And we'll address that evaluation in a later lecture in chapter 11. That what we want to do today is look, if you were looking at, say, the first strategy where there's a probability, do you understand what a probability is? But more importantly, you're going to have to evaluate your models, and none of them are perfect. They don't classify everybody correctly. They make some mistakes. You end up diagnosing some individuals as having COVID, the virus, when they don't have it. And then others, you say, nope, test came back negative, you don't have COVID, when in fact they do have COVID. We just didn't pick it up. We make some mistakes. And we'd like to know, what's the chance? What's the probability you're going to make a mistake? Those, you need to have a good understanding of probability to be able to understand both some classification tools and how to evaluate those different classification tools. To get into formal probability, we need to look at, introduce you to some of the jargon, the concepts they use, and some of the rules that they follow. And that's what we're going to do today, is get into those sorts of technical things. Probability, what is it? May seem straightforward, but it's actually, again, it's not well understood, and we don't understand where we get the probabilities from. First off, it's about a future event, the chance a future event will occur. I'll come back to that. That you might think of probability like flipping a coin. If I flip a coin in the air, a Canadian quarter, a 25-cent piece, has two sides to it, like most coins do. On one side has a face of the queen. On the other side, there is an animal with antlers, a caribou. So and the coin's a really simple thing. If I went and flipped it, I don't have any special techniques. Coins are generally fair. If I throw it in the air, I don't know how it's going to come down. Chance it's going to come up with the queen looking up at me, probably 50%. That it's based upon a belief, a theory, that both sides have equal chance of coming up, that there's nothing secret, some special way of making the queen side come up more often or less often than the caribou's. And so we call that a theoretical probability. We get them in gambling with lotteries, with roulette wheels, with some card games under certain conditions, if you're not counting cards, that we can work out the probability based upon the theory of a fairness in the game. In business, we don't have a lot of such situations. There is the case of the stock market, where if I was to predict whether a stock will go up or down tomorrow, if the stock market is fair and everybody has the same information, it should be 50-50. That's a theory that we have in finance. But In most areas of business, we don't really have theories that we can carry forward, so we can't often use theoretical probabilities. Before I move on, this one is important to illustrate why I put the emphasis, or why I underlined at the top, a future event. After I flip the coin, catch it, put it on my hand, I can peek at it, see is the queen looking up or not looking up. If we're in the classroom, I'd normally ask the class, well, what's the chance the queen's face is looking up? And frequently they'll say, well, it's 50-50, because they don't know which side is facing up. Not knowing is not the same as it being a chance event. That because I know the answer, they don't know the answer. Their probability, they're saying, is 50%. My probability is either 0 if it's the caribou, or it's 100% if it's the queen. How can we both have different probabilities at the same time about the same thing? It's because we can't. Their probability is wrong. The probability the queen's face is up is either 0 or it's 100%. You've got a test coming up on Friday that if you were to guess at one of the multiple choice questions, you have 4 responses. You could say, I don't have no idea. I'm just going to guess. And the chance you're going to guess correctly is 1 in 4, 25%. But as soon as you make your selection, say you pick A as the right answer, your answer is right or it's wrong. Probability disappears as soon as the action takes place. It only applies to the future. And this is important because when we talk about risk in decision making, we can talk about a procedure that we're using to make a decision, and this procedure is right 95% of the time and wrong 5% of the time, and so feel that it's a good procedure to use. But was it right or wrong with a specific decision? May not know, but you either made the right decision or you made the wrong decision. Once it's happened, it's over. It's no longer probability. If you have a test for COVID, some of the rapid tests which aren't as accurate, they may say the test is accurate 95% of the time. 95% of the time, if you have COVID, it comes up and says you have COVID. And 5% of the time when you have COVID, it comes up with a negative result and mistakenly tells you that you don't have COVID. We can find that out through clinical trials and that type of thing to work out the effectiveness of that test procedure. But after you apply it to a particular individual, that is the test right or the test wrong? It's either right or wrong. It's a procedure that works a certain percentage of the time, but we don't know if it worked this time or didn't work this time. It's different. Be cautious about how you phrase things. Anyway, we'll get to that. You'll see it come up as an issue in a statistics course because they use that type of methodology in stats. With that test on Friday, if I ask you what's the chance you're going to score at least 13 out of 16 on it, what would you say? Come up, you might be able to say, yeah, I think I could do that. I think it's quite likely, or it's quite unlikely, or iffy, 50-50. You may have trouble actually assigning a number, but assuming you could, where did it come from? Is it just your opinion? You've written several tests already. You may have some sense. You know the chapters it's on, chapter 7 and 8, that, and you may feel you know them well, or you've got worries about multiple regression in chapter 7. It's your opinion. It's subjective. And then we call it a subjective probability. Why would we ever use it? Well, we use it when we don't have any alternatives. We don't have a theory. we don't have a lot of experience or data to work from, that it's frequently used in scenario planning. So if you're planning right now, everyone's planning for their major rollout of vaccination, of how to administer vaccines across a large population. And they've laid out a strategy for doing it. But as we've already seen with some of these plans, they've not unfolded the way anticipated, that there was demand that far exceeded the supply. Uh, Other types of things have happened. There's been response from people that wasn't anticipated, people that decided they didn't want to be vaccinated. That we could imagine a variety of scenarios of what might happen when we roll it out, and then ask, well, what's the likelihood of this scenario happening? Those are different subjective probabilities. And we may have a plan B for if that scenario happens. So to uh, try to be prepared for the future, then that you'd like to be very well prepared for scenarios you think are likely to happen, and for scenarios that would be devastating if they did happen and you weren't prepared, but they may be less likely. But the probabilities may help you guide how much effort into what preparations you'll make for each of these different scenarios, knowing that probably only one of them is actually going to occur. But that's sort of how they're used, not what we're getting into in the course. We're going to look at the one that we're going to focus on a different probability from those two. And we're going to work with ones based upon data. And I'm going to look at an example based upon the survey. Similar, well, some questions on survey, much like you completed back in January. That survey, or a different version of it, was given last winter, it was given last fall, and it was given in the fall of 2019. So I'm using the 2020 survey in your assignment that's coming up, assignment 4. But so I got to use the previous 3 surveys from the fall of 2019 and the fall of 2020, as well as the winter of 2020. And we had 583 students that gave feedback about how often they worried about their grades and how often they felt depressed. And curious to ask questions about, well, do a large proportion of students worry about grades or experience depression or both of those things? Is grade anxiety and depression related? Are they connected in some fashion? That do those who experience depression worry more or less about grades, or those that worry about grades, do they experience more or less depression? And maybe I could measure those things in terms of proportions. What percentage of students? Percentages, proportions, those are essentially probabilities. So I'm going to give you, this is what we got out of those 3 surveys. And I've compressed it. This is like getting data out of a pivot table. And it's just frequencies that I've got here. For the 583 students, I've got 121 up here that worried a lot, but were not depressed. On the other hand, I've got 151 that worried a lot and were quite depressed, or 133 didn't worry, never depressed. So it's different combinations here that we've got. I've compressed, if you recall the question about worrying, it was really on a scale from rarely worrying or never at all to worrying almost all the time, and depression from very rare to more than once a week. I've compressed all of this into a smaller number of categories because, as I mentioned back with pivot tables, watch out for cases where you have very small frequency counts. Anything we calculate from a sample is an estimate, and if you've only got a little bit of data, you probably won't get a very good estimate. So don't have small groups. So this table that I've got in a statistics course would be called a contingency table. It describes every contingency in terms of worrying or depression and how many people fit into each. Generally, a contingency table has just frequencies, how many fit what. So I might start out asking, well, what proportion of students say they're often depressed? And what would that be? Well, I've got 583 students, and I've got 207 that say they're often depressed. So 207 out of 583 might be my proportion. And I get 36%. Okay, I like to think in terms of the fraction because the fraction I can picture 583 students and 207 of them expressing depression. 36% is a little more abstract to me. Now, how can we use this, particularly as a probability? Well, there we have to make some assumptions. There are several things that come up. If we assumed that future students were similar to those that took this course in 2019 and the fall and winter of 2020, then we could ask, well, what's the chance that a randomly selected future student, like some of you, is often depressed? That this isn't a theoretical probability. I've got no theory other than saying students from the past are typical of students I'll see in the future. It's not subjective because I'm basing it upon real data, but it is it's a relative frequency probability. It's the percentage of a sample. And relative frequency probabilities are the most frequently the ones that we encounter. But watch it. It's based upon a sample. So it is an estimate. It's not perfect. Maybe it's not 36%. Maybe it should be 33% or 38% or 39 or 40%. It's somewhere in that neighborhood. So it's not quite exact. Okay, it's an estimate. And I could get into issues about measuring precision, but I'm not going to do that. We want to focus. We've talked a lot about estimation before. I want to focus at the moment on that, just understanding the numbers, the percentages we get. We do know that if we had a bigger sample, if this was 583,000 students, then our estimates would be very accurate. I'm not going to worry about the accuracy of the estimates. I want to just understand what the probabilities represent and what we can learn from them. Backtracking a little bit, I mentioned about generalization. Using this going forward, it means that the data that we use to calculate the relative frequency is indicative of the type of data we'll see in the future. And that's probably not the case with this data set, as a caution. Students that take this course in the fall are very different from the students that take it in the winter. They tend to be somewhat older. They're more international students. There are a lot of transfer students that have some post-secondary experience, whereas the students that take it in the winter, the vast majority, are recent high school graduates. This is their second term of university, and they don't have any other post-secondary experience. Very different groups from one another. And in addition, the students that responded in the survey from fall 2019 and winter 2020, that was before COVID. The ones I've also thrown into the sample are from the fall of 2020, and that is after COVID came in. And that group was very worried about grades and the social isolation, anxiety over online learning instead of a classroom-based learning. Depression was much more frequent. The class I've got now, it in addition to be a different student mix than in the fall, also are experiencing their second term of online classes. So maybe they've settled into a routine and got made some adaptation to that environment. Or there may be other issues. Students in the winter tend to have more students in the winter are depressed than in the fall. I don't know if it's sunlight deprivation or what the issue is, but depression is generally increases during the winter months and decreases during the summer months. That uh, I had some students last fall that when asked that they were experiencing a lot of anxiety, asked if they thought they were going to make it through the term, they said, yeah, I think I can handle it. I can cope that long. But I'm worried I'm going to fall apart in the winter, that I won't be able to keep it together that long. That's too long in this closed in environment. So it may be that so it's different. So the past and the future may not be connected. So we should be cautious about generalization. Generally, with businesses, that they are looking at uh, predicting customer behavior or transaction changes that are based upon tens, hundreds of thousands of pieces of information that they have acquired in the previous few months. And they're trying to make predictions about what's going to happen in the next few months. So the time span they're looking at from beginning to end is relatively short. So it's recent data they're using to predict events that are going to happen fairly soon. And except for disruptions, sudden ones like we've seen with COVID, their models should work reasonably well. That the relative frequency should be good predictors of the near future. And because they've got so much data, they should be reasonably accurate predictors. But let's get back to our little sample and get into treating this as probabilities. Okay? That again, why? It's why do we need it? Why do people in business need this? That probabilities describe risks in decision making, and every decision involves risk. Every decision you make could be the wrong decision, and you have to appreciate the risks that you're trading off in making a choice. And as mu- no matter how many decisions someone makes, their formal understanding of risk or probability is generally fairly low. Most people don't understand or appreciate risk. And even when they know the risks, the decisions they make are not always rational. And we'll look at a little bit of this next class. Actually, I forgot about it, an example of people not understanding probability and risk. And that we'll also look at some of the psychology of risk later on when we hit evaluation. But we're going to leave that for now. But it's important you really have a good grasp of this. Let me get into the jargon. That's what I said at the beginning. I'm going to look at the language that's used in probability and some of the notation or the symbols we use. So here's my frequency table or contingency table. And if I wanted to know what's the probability of a student being depressed, that 207 out of 583, I would generally write that capital P to represent probability, and then in brackets, the probability of what? So probability of depressed, I'll have a capital P, and in brackets, I'll write depressed. Or I might just write the letter D and have identified elsewhere that D represents being depressed. Don't be hesitant about writing things out in longhand or expressing it with words instead of symbols. So the depression is viewed as an event. It's something that happens. So I'm talking about a future student. I'm reaching in to this large pool of 583. Imagine them all in a big room, and here they are in the room. Okay, and I've taken the room, I've put a divider down the center of the room and said, okay, all those who worry a lot, go to the left. All those that don't worry much, go to the right. That those that experience a lot of depression move to the front of the room. Those that experience very little depression move to the back of the room. Those that are sort of in between, you can stay in between. So here we're in a great big gymnasium or something, and they've organized themselves essentially into 6 little groups. So if I close my eyes and I go in and I grab one individual at random, what's the chance that the person I grab is someone that's depressed? That's the probability I'm looking at. Okay? Now, if I was to ask, what's the probability that the student worries about grades and is depressed? That's this group of 51 here. Oops. Well, that this is known as a joint event. So sometimes you hear the word joint event. It's when 2 or more things all happen together that you've described. And that was, in this instance, an and. If you were to use symbols, the mathematicians would use this upside down U. If you have encountered sets and Venn diagrams and the like, this is known as intersection. I hate Venn diagrams. If you want to talk about intersection, I think of an intersection being where 2 streets cross. Where does Roby Street cross with Quinpool Road? Well, that here's Quinpool Road going down, and here is Roby Street, going across. Where do they intersect? It's these 151 people. And I divide through by the 583, and I get 26%. They worry a lot, depressed a lot. Okay? You're going to notice that my number is just a simple percentage. What is that? Let me just get a calculator here. If I were to take 151 and divide it by 583, I get 25.900, a whole bunch of decimals. Never carry more than 2 significant digits. That if this number was 20% or 30%, I don't think you'd care. They're both about the same. We have trouble knowing that it was 25.9 instead of 26% is not useful information. Okay? That just round it off to 2 digits and be done with it. That and most people like percentages instead of decimals. They don't like, what's 0.26? That 26% they can picture. They can think of 26 out of 100. That I tend not to use that symbol. Again, lots of people don't know what it means. My preference is to use the word and, worry and depressed, like I've got up here. Or I get lazy and I just put the 2 of them together and write WD. And most people recognize immediately that must mean both of them together. Keep it simple. You've heard me say that enough times. Another term that's used is the word complement. Complement is used in the context of not, an opposite. That a complement, if I spell it with an I here instead of an E, is saying something nice about you. That you're smart, you're pretty, I like you. It's a positive statement, a nice thing about you. That with an E, it means sort of like they go together, they complement each other. You might talk of individuals that complement each other. Strawberries and whipped cream complement each other. Red wine and cheese complement each other. They go well together. Another thing that goes together is opposites. That the opposite of worry is to not worry. So they go together. That if you're not one, you're the other. And If I told you that 40% of students did not worry, then you would know that 60% must worry. One is the opposite of the other. And you get a really simple formula, but it's important that you worry or you don't worry. So if I add the probabilities, I must get 1. I can't get less than 1. That means somebody's missing. I can't get more than 1. It means I've double counted. Okay? Another term that's used is or for those people that love Venn diagrams, silly people, it's the word union. So if I worry or are depressed, so if I'm in this column here among these 350, or I'm in this row here among these 207 that are depressed, I'm one or the other, or both. Okay? So it's not an exclusive thing. I'm not saying you just worry or you're just depressed. I'm saying one or the other implicitly says also both. So I could just add them up. These 120 plus the 78 plus the 151, add in the 56. So here I am, the 121, the 78, the 151, and the 56. Add them all up, I get 70%. Okay. Another way of looking at it is to go and say, well, 350 worry, and over here, 207 are depressed. So I've got those two, but those totals, both of them include the 151 twice. So I can't count them twice. So I got to take one of these bunches out. So I've got 350 plus 207. I'm going to take out the 151 that's double counted, and I still get the same 70%. It gives me the same answer. But this way, if you look at it, suppose I divide everybody by 583. That's what I did up here. I took each of those numbers, divided them by 583, rewrote it as 3 fractions. And the first one, this first bunch here, is really the probability of worrying. 350 worry out of 583. And this represents those that are depressed. 207 out of 583. And then I'm subtracting off those that are both. So I get a rule out of this. The probability of W or D is the probability of W plus the probability of D minus the probability of both. Take the worriers, those that are depressed, subtract off those that are both. And you get your probability of one or the other. I'm giving you formulas. Most of the time you don't need to use them. We didn't use this formula just a minute ago. We just looked at the table and got our answer. Most of the time, that's how you can solve these. We're now moving into the ones that are tricky. What's the chance that a depressed student worries about grades? Now, it's important that I'm looking only at depressed students. I'm only looking, excuse me, do it this way. I'm only looking at that row. I'm not looking at anybody else. We know 151 of them are worried. So this probability is 151 out of 207, or 73%. Symbolically, we write this as the probability of worried given depressed. That given you know that they're already depressed is the jargon that's used. So we write that as, what do you know for sure? Put that over on the right. They're depressed. Put a vertical line, and then on the left of it, what are you trying to find out? Well, are they worried or not? So what you don't know goes on the left. What you do know goes on the right. Okay? Some people like to think of this as a fraction. So like here, 151 out of the 207. So on the right, under the dividing sign, put the number that fit that description. So divided by 207. And on the left, the one that fits the description you're looking for. Some people like to think of it as a formula. If you were to write a formula, you have y equals some function. So what you're trying to find out is on the left. What you know, what goes into the formula, goes on the right. And if I look at the numbers again, if I divide top and bottom by 583, I get the probability of both worried and depressed. And on the bottom, probability of depressed. So I've got a new formula. Let me rewrite it as probability of worried and depressed is worried given depressed times probability depressed. This may not seem obvious now that it may have been easier with the addition rule we had before, but we're getting another rule here. If I flip the question around, so I'm looking at those that are worried, that we want to know that a student who worries, what's the chance that student is also depressed? So we know that we're looking at worried students, trying to predict whether or not the student is depressed. 151 has both characteristics out of 350, because we're only looking at depressed or worried students. You get 43%, fine. But if you look at the formula I've just created, I end up seeing the same expression written two ways. Chance of being depressed and worried, or worried and depressed, whichever way you want to say it, is depressed given worried times worry, or it's the probability worried given depressed times probability depressed. You can do it either way. And both of these we call our multiplication rule. We can multiply things together to get this combined event. So the other one rule was calculate a probability that was an or, a union situation. And this is a formula for calculating that joint event, that intersection of two things, of depression and worrying. That don't get too bent out of shape about this. We just worked out probabilities a second ago without any formulas. Most of the time you don't need formulas. There are other devices we can use to help organize information so that you can reason out how the probability should be calculated without resorting to formulas. Formulas, I think, hide the logic because people just don't, they have trouble relating to the formula. So there are other ways of doing it, like pulling it out of the table, or sometimes we may have to build a table. We'll get to that. There are some special cases. A particular special case is called independence. So if the probability that a worried student is depressed is the same as the probability of any student being depressed. So in this case, I know that the student is worried. What's the chance they're depressed? Over here, I don't know anything about their worrying behavior. I just want to know what's the chance they're depressed. If those two things are the same, then worrying gives us no new information. Okay, it's useless. They're unrelated. It's like when we were trying to predict credit card balance, knowing the marital status of the card holder, knowing how many credit cards they had, and knowing what their age was, didn't give us any new insight about the credit card balance. When those sorts of things happen, we say the two events are independent of each other. They're not related to each other. Okay? In our problem, we worked out depressed given worried a minute ago is 43%. We also calculated the probability of being depressed is 36. They're quite different from each other. So students who worry seem to be more likely to be depressed than students in general. We'd say there appears to be a relationship between the two, between worrying about grades and depression. We would say that these two events are not independent. Okay? They are, now, we didn't say they're dependent. We just said they're not independent. that what we found is correlation in a sense, but not causation. The reason they say not independent is because the word dependent suggests causation. It says that one depends upon the other. And we don't know that. It may be something else that's causing both of them to happen. We just know there's there's a connection between the two. I still wish they didn't phrase it the way they did because, and I'll get to this in a minute, but for me, I look at independent and I think of the IN at the start of that word, meaning not. Independent means not dependent. So not independent is the same as saying not dependent. Uh, and we're always taught you don't say double negatives. You don't say the same thing twice. They cancel each other out. We'll get back to this one. But this is the choice of language used, that when they're not related, they call it independent. The other piece of jargon that gets students confused with this, and I can admit that when I first did probability in the first exam I had involving probability, I blew the exam. And part of it had to do with some of the jargon being used, this idea of independent, and this other word, mutually exclusive. Mutually exclusive means they cannot occur together. So you can't be worried and depressed at the same time. Well, let's look at a table. Worrying and being depressed or not depressed, or depressed only once a month, or not worrying. We've got students that was in every one of the boxes. So all of these pairs of events that you want to look at here are not mutually exclusive because they've happened. But we do have mutually exclusive things here. If you're worried, you're in this column, then you can't be in this column. You're in one or the other. Or if you're never depressed, then you can't be depressed. It's one or the other, or you could be this third choice. So rows in a table should be mutually exclusive. Columns in a table should be mutually exclusive. And watch it. Sometimes we have trouble with that. If I was looking at products that customers bought, did or didn't buy, or they, if I was looking at gender, here's one that's really messy. This was gender, and this was what program you're in: arts, business, science. A student, when they're first admitted, can only get into one program. When you applied for admission to St. Mary's, you had to pick one program to be admitted to. Once you're enrolled, though, you can add a second program. So if you came in the business program, and now you also want to do computing science alongside it, you could do a Bachelor of Science and a Bachelor of Commerce at the same time. So you could be in two rows at the same time. And today, with gender, once upon a time, we insisted that you declare yourself as being male or female. Society has become more open on that, and you can be male, female, both, neither. You can. There are all kinds of different categories we can put you into, or you can put yourself into, and you can put yourself into multiple categories in terms of gender. So the columns are no longer mutually exclusive. But mutually exclusive is when you can't be in two things at once. For myself, I get confused on the two because I grew up in Quebec, and particularly in the 1960s, that was when there was the first strong movement, very visible movement at least, of Quebec wanting to be separate from the rest of Canada. And we had separatist organizations that were used terror, so I guess you could call them terrorist organizations, that there were bombings and that type of thing, and in 1970 we had kidnappings as well. That regrettably over the years people did get killed, not mass numbers, but still anybody being killed or injured is a tragedy. That, but we call them separatists, and because they wanted Quebec to be separate from Canada. That so we would think of you're either in Quebec or you're in Canada, but you cannot be in both. So that they were separate in that regard, mutually exclusive. But you could also argue that they wanted independence, that they didn't necessarily insist on being a separate country, but they were autonomous in their decision making. So Quebec could make its own choices about things without Ottawa having a say in their future as well. And in that regard, you would say that their decision making by Quebec was unrelated to decision making by Ottawa. So they were independent in that sense. I viewed the words independent and mutually exclusive as being the same thing. And many students, I think, get confused on that. Don't get so tied up in the jargon. Mutually exclusive, we don't use very much. Independence, relationships, yes, that's important. So be careful. Often the tables that we've had, I had a frequency table there. We don't use frequency tables. They are used in the stats course because of the way they manually do calculations and the like. But they're hard to interpret because if I was looking at 151 students that were worried and were depressed, or 207 that were depressed, I'm asking 151, is that a big number? 207, that's a big number? Well, it does seem like a big number. But it's out of how many? Is that out of 500 or 5,000 or 5 million? You need to think of it relatively, like we've been calculating relative frequencies. A probability table is one where we convert those frequencies to probabilities. And so we'd get a table like this one. So the 36% over here, the 207 out of 583 is now 36%. The ones that weren't worried, there were 40% were not worried. That was 350 out of 583. We had ones that were worried and were depressed. That was 26% of the 583. If I wanted to know what's the probability that you worry given depression, so given you're depressed and you're in this row, I could think of it as 26 out of 36. And that works, that probability depressed and worried divided by the probability of depression. So even that formula, but you, these, in a probability table, everything is scaled. So the total, imagine it as a total frequency count being 100. Okay, so I've only got 100 students, and this is how they broke down. And that may be easier for you to interpret. The rest of it, in terms of any calculations of other probabilities from the table, some you can pull directly out, like the 36% or the 26%. Others you can reason out the same way. 26 were worried and depressed out of the 36 that were worried or that were depressed. So 26 out of 36 or 70% or 73%, whatever the number was, is the probability of worry given depression. In a pivot table, this would be if we showed values as a percentage of the grand total. Useful, but actually in practice, if you're presenting results, you often don't do it this way. You do what we did in assignment 2, where we looked at percentage of row total or percentage of column total. The rows reflect levels of depression. So like this entry is the percentage that are worried given they are depressed. And that was what we calculated earlier, that 73% of those that are depressed are worried. And so among the depressed group, what percentage are worried? Among the not depressed students, what percentage are worried? So we can see that as depression increased, worrying increased. And the level of worry did. So we can see that relationship more strongly. And that's what we looked at in assignment 2, was looking at those. They were conditional probabilities that we calculated or had in our pivot chart. Similarly, if I looked at the columns, that would be looking at within the groups of levels of worry. So that among those that worried, what percentage were not depressed? So among those that worried, 35% were not depressed. Among those that didn't worry, 57% were not depressed. Okay? So not being depressed is much more common among people that don't worry. Whereas if I was looking at what percentage are depressed among those that are worried, it's 43%. But if I look about those that don't worry, it's only 24%. So there's quite a shift between those two. That, again, it's a conditional probability that I've got here. And as I warned you back with pivot tables, communicating that may be more valuable information than a probability table shows, but it's very easy for people to get things mixed up. They can't quite understand, are you looking at depression among those that worry or worrying among those that are depressed? And we'll address that confusion a little bit more in next class. So just to summarize, we've got a lot of jargon. Probability has to do with an event happening in the future. The probabilities have different sources. They can be theoretical, like in gambling, subjective, it's your opinion, maybe the opinion of an expert, but it's still an opinion, or it's ones that is really rooted in data, in which case it's a relative frequency. A joint event is when two things happen together. So we've got this and statement here. We can have cases where we're looking at one or the other, union of two events. We have a symbol that we use for complement when we're looking at the opposite. So if A happens or A does not happen. The important ones for us, the most valuable ones for us, are conditional probabilities. The chance of A happening when we know stuff about B. Talk about this a little bit more in a minute. That and this, we often get confused on this. Independence is when B doesn't give us any information about A. That they seem to be unrelated. Again, it's going to be important. I wouldn't worry about mutually exclusive, except if you're building a table, make sure your rows or your columns are mutually exclusive. And we got formulas. Rarely do I have to use a formula. It only happens if I give you a bunch of probabilities and then you have to reason out some other probability. Those tend to be like puzzles. I can't give you simple strategies for addressing those puzzle questions. And why should you be an expert at solving puzzles in probability? Understanding tables is important. We're going to look at another device called a tree where we're going to be using the multiplication rule. And you'll see it makes perfect sense, and you don't even know you're using it. Why do it in data mining? Well, that we're trying to predict an outcome based upon knowing pieces of information. So I want the chance of that outcome happening given the information I've got. That's a conditional probability. So a logistic regression is really calculating a conditional probability, chance of an outcome given information we know about customers. And so conditional probability is important for building those classification models. It's also important for doing the evaluation of how good a model is. And we'll see that when we come to it. So the next class, I'm going to use trees. I've mentioned them. It's a way of exploring conditional probabilities when you're given that information at this outset. I'm going to use a formula called Bayes' rule that switches A given B to B given A. But again, we don't need formulas and rules. We can reason this out if we understand where stuff is coming from. And the other is going to challenge you on making sure you understand conditional probabilities. Do you have it the right way around? Is it A given B or B given A? Do you understand the difference between the two? Because they are very different from each other. I hope this recording worked, but this is where we're going to end here. Thank you very much. And let's